Hello, Level 12 Physics. Today's lesson will be on scalars and vectors. Okay, so the first question is, what is the difference between scalars and vectors? So I want you to pause the video now and have a little think about that. Okay, so here is a table with some examples of scalars and vectors. Okay, so you can see that scalar quantities are things like mass, length and distance, whereas vector quantities are displacement, velocity and acceleration. So again, I want you to pause the video now and have a little think of what is the difference between a scalar quantity and a vector quantity. Okay, welcome back. So you may have worked out the difference between a scalar and vector quantity is that a scalar quantity has a size or magnitude, whereas a vector quantity has both a size and also a direction. So for example, velocity, it has a size, but also you move in either direction away from a point or towards it. Okay, so when using vectors, there are many mathematical operations that you have to do in order to use them, and one of them is multiplying a vector by a scalar quantity. So in short, multiplying a vector by a scalar simply multiplies the size of the vector by the size of the scalar quantity. And this results in a new vector with the same direction, but the magnitude is the product of the two vector and scalar quantities multiplied together. So here's an example here. Here we have mass 1, the force being the first mass times the acceleration due to gravity. And here we have a second ball here which has 2 times the mass. So simply the force of the second ball, because the second mass has twice the mass of the first ball, will be twice. Okay, the force will be doubled because the mass has doubled. And this is what we see here. Because the second mass is twice the mass of the first ball, then the force due to gravity of the second ball will be twice the force due to gravity of the first ball. Okay, so resultant vectors occur when you add two or more vectors together. Okay, there's a single vector that has the same effect as all the others put together. So here are some examples of vector addition. If you have, say, a velocity of 5 meters per second added to a velocity of 5 meters per second, then the resultant vector is 5 plus 5, and also in the same direction as the two previous vectors. In the second example, because it is a negative velocity, the 5 plus negative 5 will give an overall direction of 0. It'll stay in the same place. Whereas something like example 4, when you have the second vector being minus 10 meters per second, 5 plus negative 10 means that it will be negative 5 meters per second, which means it's reversing. Okay, and the same example kind of stands for the last example where it's going 10 meters per second up, for instance. There's a force acting on it of minus 5 newtons, so the overall force is 5 newtons, for example. Okay, so here's a little animation of 3 different planes. In the first example on your left, you have a plane which has a tailwind. Okay, on the second example in the middle, you have a plane with a headwind. And the final example, you have a plane which has a crosswind. And you can see that the direction of the plane is different for each condition. Why is this? I'm going to go through them individually. So it's all down to relative velocity. The plane travels with a velocity relative to the ground, which is a vector sum of the plane's velocities relative to the air. So it's taking into consideration the wind velocity. Okay, so it's the plane's velocity plus the wind velocity. So in the first example, the plane's velocity is 100 kilometers an hour. It gets a bit of a tailwind of 25 kilometers an hour. So all you have to do to get the resulting velocity of the two combined is add the two. 100 kilometers an hour plus 25 kilometers an hour gives 125 kilometers an hour. Okay, in the second example, the plane's velocity relative to the surface is 100 kilometers an hour, but this time it's got a headwind of 25 kilometers an hour, so you're taking it away. So it'll be 100 kilometers an hour plus minus 25 kilometers an hour, gives a resultant velocity this time of 75 kilometers an hour. Now, the final example is where you're combining the horizontal and vertical components, okay, and you're using something from a few years ago called geometry, using Pythagoras' theorem, okay. So in Pythagoras' theorem, you've got 100 kilometers an hour going down, you've got a wind velocity of 25 kilometers to the right, so all you do is, using Pythagoras' theorem, you add them, okay. Now you notice also when you're adding vectors that they are added, when you draw them, nose to tail to get the resultant vector here. Okay, so how do we get to 103.1, I hear you ask? Well, using Pythagoras, simply 100 squared plus 25 squared. Okay, you get the sum of that, and then you take the square root of that, and that will give you your answer of 103.1, and remember the units, kilometers an hour, and that's the answer. Okay. So this is an alternative way of doing vectors. It's called the parallelogram method. So you have your one vector here, and another vector here. You place them tail to tail, not nose to tail, and you place them 90 degrees to each other. Okay. And then you go to the end and you draw again another line 90 degrees, and again here draw a line across there which is 90 degrees to the tip of the first vector. Okay, and where they add, where they combine, is where you will draw the resultant vector. Okay, that's called the parallelogram method. I don't mind which method you use, as long as you're attempting them, as long as you get the right answer. It's up to you, and both are acceptable. Okay, so the next thing is resolving vectors into their corresponding components. So any single vector can be represented by two other vectors, known as components, which would have the same effect together as the original one. Okay, these components are usually the vertical or y component and the horizontal component or the x component. Okay, so you can break them down. This is where your friend again, trigonometry or geometry, comes in with SOHCAHTOA, where the sine of the angle theta here is simply the opposite, which is this one here over the adjacent, or cosine theta is the adjacent over, this time, the hypotenuse, or tan theta is the opposite over the adjacent. Okay. So this is a quick example employing Fido, who's walking around Auckland Domain on a leash, as an example of resolution of vectors. So here we have Fido being pulled on his chain. There's a tension force of 60 newtons, and you have to work out both what the vertical component is, and then once you worked out that, you can work out the horizontal component. Okay. So, how do we do that? Well, let's use our friend SOHCAHTOA. So we draw a triangle for the problem. If you want to work out, to start off with, the vertical component, we know that the hypotenuse is 60 newtons. Okay, that's the hypotenuse. And we know that the angle is 40 degrees. Okay, that's theta. There we go. And we want to know the vertical component here, which is, in this case, I'll call it x. Okay, so we use SOHCAHTOA. Right. So we want to find out the value of x, which is going to be the opposite side of a triangle. So we can only use sine because we know the hypotenuse, which is 60 newtons, and we're trying to find the opposite. Okay, so sine 40 will equal the vertical component of force, which we've called x, divided by 60 newtons, the hypotenuse. Rearranging the equation, the vertical force is going to be 60 newtons times sine 40, giving us the force in the vertical direction of 38.6 newtons. Okay, so that gives us that value there. So then how do we get 45.9? Well, we know again that we know that we want to know the adjacent, okay, which is up here, right? So we know the hypotenuse, okay, so we use cosine this time. So the cosine of 40 is this time the horizontal component that we're trying to find out, divided by 60, because we know that is the hypotenuse, so it's adjacent over hypotenuse, where that was opposite over hypotenuse, okay? And rearranging the equation, the horizontal force will be 60 newtons times 40 degrees, or cosine of 40 degrees, giving the horizontal force as being 45.9. So geometry, you may have thought was useless in year 10 and 11, comes in handy in year 12 physics. Okay, so exercise 1, what is wrong with these diagrams? So in diagram A and diagram B, I want you to pause the video now for 5 seconds and have a little think about that. Okay, so welcome back. So remember I said when you're drawing vectors using the first method, it needs to be nose to tail. Okay. Okay, so A here is the first vector, B is the second vector. In that case there 2. So let's have a look if we've done the rule. Okay. So here we have A and B combined. You'll notice that it's actually tail to tail. So it doesn't, not the correct way of drawing it. In example B, here we have head to head. Again, not right. You need to draw your vectors nose to tail. Okay. Pointing out, of course, that when you're drawing these vectors, the length of the vector equals the size or magnitude of the component, and you need to also put a tail, which is direction of the vector. Direction. Okay. Moving on, exercise 2. The diagram on the right depicts a force which makes an angle to the horizontal. This force will have horizontal and vertical components. Which one of the choices below best depicts the direction of the horizontal and vertical components of the force? I want you to pause the video now and have a little think about that, unpause it and see if you're on the right track. Helps to draw diagrams for this. Okay, welcome back. Let's break it down. Okay, we'll look at A first. So if we draw the vertical component and nose to tail, of course, there we have the horizontal component. You will see the resultant vector here goes in that direction, so it can't be A. Okay, looking at B now, we have the, again, vertical component and nose to tail, again, B there, goes in that direction, so it can't be B, because looking for this, so bump bar for B. Looking at C, we have again vertical component going up, head tail again, and we have this way, so again it looks nothing like that, so it can't be C, so the only answer must be D. I'm just going to verify that by drawing a diagram similar to the plane example we had earlier. nose to tail, and lo and behold, the vector works, even though it's a bit squished. Okay, so D is the right answer. Okay, so here's the third example that I want you to work on. So consider a tow truck to the right. If the tensional force of the cable is 1,000 newtons, and if the cable makes a 60-degree angle with the horizontal, then what is the vertical component of the force which contributes to the lifting of the car off the ground? Okay, so I want you to pause the video now, have a little think. I suggest you use some diagrams and come back to the video and see if you've got the right answer. Okay, so the way I do it, might not be the way you do it, that's the way I'm going to do it. So I'll just look at the values I have. I have 1,000 newtons, and that's the tensional force, and it's a 60-degree angle from the horizontal, so I would start drawing a triangle. Okay, so we got your 60 degrees here. We know that's 1,000, and we want to find x, the unknown, the vertical component. Okay, so I'll go back to my wonderful SOHCAHTOA, tried and true, and work out which one's the best one for this little tool. I see physics as a bit of a toolkit. They've got a series of toolkits. What tool you're going to use? In this case, it's going to be trigonometry, a bit of geometry. So we know 1,000. We want to find this. So this is the hypotenuse. As we know, this is the opposite. So the only one we can really use is sine. Okay, so let's see if that works. So sine of 60 degrees equals the opposite, which is our unknown, the vertical component divided by 1,000. Okay, we do a bit of a rearranging of that. So that means that 0.866, which is the sine of 60 degrees from my very mathematical brain, times 1,000 by rearrangement will give you the answer of 866 newtons. Okay, and that is the answer. So hopefully you got that right. If you didn't, let's see if you can work out where you went wrong, and if you can't, come and see me. Okay, so the final example we're going to use is exercise 4, where the sine has a mass of 50 degrees, and you need to determine the tension force here on the cables. Okay, so it's a tricky one, so I'll give you a few moments to pause the video and think about it and come back if you think you have an answer. Okay, so looking at the question, we have the sine having a mass of 50 kilograms, yet we're discussing forces, so we've got to find a way to convert a mass into a force. And what we're going to do is we're going to use some of Newton's second law, where force equals mass times acceleration, and the special force associated with mass, of course, is weight, which will give a value of a W, and that equals the mass times gravity. Okay, and that's the acceleration due to gravity, and I'm going to give it the value of 10 newtons per kilogram today, but in the exam it might be given a different value, but just like last year, we'll give it the value of 10 newtons per kilogram. Okay, so that means that the vertical component, the weight force, is going to be 50 times 10, which equals 500 newtons. Okay, with this information now we can start working on a triangle. Okay, not a very straight triangle, but there's a general idea. So this we know is 45 degrees, We know this is the value that we want to find out, which is your hypotenuse, and we know that the vertical component is going to now be 500 newtons. Okay, so then we go back to the little mantra I'm sure you're getting quite bored of, but it's good to get over it and use it. So, ka toa, and we delve into our toolkit. I see physics as being a series of little tools you can take out of your toolkit and work on problems. And let's see which one's best. Okay, so we want to find H. We know the opposite side is 500 newtons. So the best one to use would be sine. Okay, so sine of 45 degrees will equal the opposite, which is 500, divided by the hypotenuse, which we don't know, which is x. So therefore, rearranging, x will equal 500 over the sine of the 45-degree angle, which equals 500 over 0.707, and the final answer you should hopefully get is 707 newtons for your tension force. Okay, so if you got that correct, pat on the back. If you didn't, see where you may have gone wrong just by going through the problems. If you're still having trouble, come and see me. Okay, so that's about enough for vectors for today, in fact for the week. So in the next few lessons we're going to be applying these vectors into problems involving motion.